What's going on, everyone? Welcome back to another video for the AI for Aspiring Researchers lecture series. Today we're going to be going over deep neural networks for the MNIST dataset. Now, you might already remember the MNIST dataset. Basically, it's just a handwritten digit dataset that we can train on these neural networks in order for kind of predicting what exact number is shown in these images. So let's jump right into it. Alright, so the first library that we're going to import is a new one, which you might not have seen before, but is a really important one in the field of machine learning. And it was developed by Google. It's called Tensorflow. So we're going to say import Tensorflow as TF. Now what Tensorflow allows us to do is create these neural network models much faster and much easier. And the code is way more simplistic to use. So we'll be using Tensorflow. Okay. Then we're also going to say import matplotlib.pyplot as plt. Oops, plt. Okay, so for the reason for this is basically just to show you guys how these digits look, and also to show you in the very end the graph of the validation accuracy over time, or how well our neural network is actually performing. So we'll be plotting those values. Okay, then we're going to say from tensorflow.keras import datasets, layers, and also models. And so you'll be seeing basically what these are for. Datasets is just to allow us to download the MNIST data. Layers is basically to kind of create the different layers of our neural network, and models are basically to create our neural network model, and you'll see exactly how these are used in just one moment. Okay, from there we're going to say from keras.layers import flatten and dense. Okay, so what these are for, flatten basically means when we're getting this data, we're getting it in the shape of a 2D array, right? Because these images are squares, or they're square images. So a 2D array represents each single pixel. And so what flatten does is it basically takes this 2D array and makes it into a one-dimensional array that we can then feed into the neural network. And dense is basically just each layer in our neural network has to have a certain amount of nodes. And the dense, what that means is it's just how many nodes are in that one layer, and you'll see how that's used also. Alright, so let's go ahead and run that. Okay, now what we need to do is we need to import our actual data. We need to load the data. So what we're going to say is train underscore images, train labels, or let's actually just call this train X and train Y. I think that would be easier. Train X, train Y, and then we're just going to say test X and test Y. Right, so the X's are basically the images of these of these handwritten digits, and the Y's are the actual values for them. And then we're going to say this is equal to our data sets. Remember, this is what we imported earlier. .mnist .load or load underscore data. Right, so this is just going to load in our data and store them in these variables: train X, train Y, test X, test Y. Okay, and one more thing that we need to do, we also need to normalize the pixel values between 0 and 1. And the reason for this is because if we don't normalize it, our model will not work, or it'll take a significant amount of time to actually reach a good kind of model, or something that predicts well enough. And the reason for that is because when we run our model, this gradient descent algorithm is not going to be moving it as much in terms of those values relative to what they were to start off with, right? So if it's moving 1 relative to 255, that's not really doing much, and it's not really giving us a more accurate prediction with our model. So what we're going to say is train images. So we're going to do this to our train X, I should say. Train X and then test X. So these are the images. We're going to set that equal to then the same thing, but each one divided by 255. And the reason for that is when we import these values, you're going to get for each pixel a value between 0 and 255, right? And the reason for that is because each value can either be white or black or somewhere in between. And so when you see those values, you'll see that each color or each shade of gray has a different number associated with them, and it ranges from 0 to 255. So we have to normalize it in order to get to 0 and 1 by dividing by 255. Okay, so let's go ahead and run that. Right, so you see this downloaded the data set. And now, before we actually build our neural network, I kind of wanted to show you, if you don't all kind of remember, what exactly these MNIST digits look like. So we're going to say plt.imshow, which is just short for image show, and then train x, and we're just going to say 0, so this is the first image, and cmap is equal to plt.get cmap, and then we're just going to say gray, because it's in grayscale. And you'll see that, right. Okay, so this is essentially the first image in our data set, and you can see clearly that for the human eye, we can recognize this as the number 5, right? We can also try 1, also I'll just put in a plt.show to get rid of that first line. Okay, right, and so the second image, or the first index, is representative of the number 0, right? You can clearly see the number 0, and you can go on and so forth just to kind of see what these numbers look like and kind of test them out for yourself. Okay, but for now, what we're going to do is we're actually going to start creating our model. Okay, so the first things that we need to do is worry about the hyperparameters of our neural network. Now, what hyperparameters are, they're basically values that have to be set before actually running the neural network, because you can kind of think of them as the physical attributes of this neural network, right? So things you might have heard of, like the learning rate, how fast a neural network learns, or the dropouts. Basically, what is the dropout number for each of these different layers, or the batch size. These are the 3 hyperparameters that we'll be working with right now. So what we're going to do is we're going to set our learning rate. Our learning rate is equal to 0.01. Typically, a learning rate is around this value. It's not too big or too small. And the reason for that is you want that nice, like, medium value so that your model doesn't kind of overshoot the local, or the global minima, I should say, or undershoot it to take a lot of time to get there. And so the 0.01 is typically the value used. Then we're also going to say dropout 1 is equal to 0.1, or sorry, 0.2, and we'll just copy that 2 more times, and we'll say dropout 2 and dropout 3, okay, 2, dropout 3, and basically what we're saying here, oh, this should be equal to, okay, so if you don't know what dropouts are, basically what they're saying is that at random, choose some nodes to just eradicate from the entire neural network, or don't consider them for some time in the neural network. And what that allows us to do is kind of create this more random process that gives us a more optimized value, or theoretically a more optimized value, because we're not kind of overfitting on some nodes specifically. And then what we're also going to say is a batch size is equal to 128. Now it's fairly arbitrary. Usually for batch sizes you choose values that are powers of 2, so you could say 64, 128, 256, so on and so forth, or you don't even have to give a batch size. Sometimes, or at least in the case that we're doing, it can also automatically predict a batch size for you. Okay, so now let's actually go ahead and create our model. So I'm just going to say, put a little note there. Let's just say create our deep neural network. Okay, so now what we want to do is actually create these models, and what we're going to say is model is equal to models.sequential. Now what this is going to do is it just means in a sequence. So you'll see later on that there are other types of models. This is one of them. A sequence just means that one layer goes to the next layer, goes to the next layer, so on and so forth, until the very last layer. Okay, then we're going to say model.add, and then layers.flatten. So remember I said flatten was basically taking in our, it's taking in our image and creating it into a 1D array. So we're going to say input shape is equal to a 28 by 28. And the reason we're doing that is because these images, or the MNIST dataset, all these images are 28 by 28 images. And so we want to flatten it and put that in our respective input shape. Okay, now we're going to say model.add, and then we're going to go ahead and say layers.dense, and then 128, and an activation of ReLU. Leaky, or no, not leaky ReLU, just ReLU. I forgot what that stands for, but basically what it means is that this activation, it'll kind of have this sort of shape if you're following my mouse here, like that. But the main point that I want to focus on this line is this dense. What it's basically saying is that this is going to be our first real layer in our neural network, our first hidden layer in that neural network. And this hidden layer has a total of 128 nodes. Now this activation of ReLU, you can choose different values. ReLU is typically the one that's rectified linear. That's what ReLU stands for, by the way. And you can choose different values for activation. I believe there's like sigmoid. That's another popular one. Leaky ReLU. Those are some other ones. You can go ahead, test them out. For now, let's just stick with ReLU because it's probably the most popular one. Okay. Anyways, now we're also going to say model.add layers.dropout, and we're going to go ahead and say dropout, dropout 1, right? So this is going to take our first dropout value and put it kind of respective to our first layer. Now I'm going to go ahead and copy these past two lines because they're all going to be very similar, and I'm going to change these values to 64 and 32. And the dropouts from dropout 1 to dropout 2, and the second one to dropout 2, or 1 to dropout 3. Okay. Right, and now the last layer is going to be just model.add. So the last line in our model really is just going to be model.add layers.dense, and then, I should say layers.dense, and then 10, and our activation is going to be a softmax activation. This is important. So basically this is the last layer of our model, and our last layer is going to have 10 nodes, and this is a really specific number because in our data set there are only 10 digits, right? 0 to 9, those are 10 digits. And so the neural network should only be predicting a value from 0 to 9, and basically those 1 of 10 different digits. So that's why we have 10 there. 10 is essentially the total number of outcomes that you could have, or the neural network could predict. And what this softmax is basically saying is the neural network is going to predict different values or kind of percentages as to what it thinks this digit is. So it might say, I think this 0 over here or it's a 0 with a 50% chance, or 0.5, and then it might say, oh, I think it's the number 2 with a 0.2, I don't know, something random. But basically what softmax then does is it takes these different values for all their possible outcomes from 0 to 9 and takes the maximum of those values, or the maximum prediction of those values. So in this case, if it predicts the value 0, then the value in that last node corresponding to 0 would have the highest probability. Right, and that's what softmax then goes ahead and chooses. Okay, now we're going to say optimizer is equal to tf.optimizers.atom, and then we're going to go ahead and say learning rate is equal to our learning rate that we defined earlier. Learning rate. Okay, so I think right now I'm using TensorFlow 2.0 because this is on a Google Colab, but if you happen to still be using TensorFlow, like one of the first version, instead of optimizers.atom, if I'm not wrong, it should be tf.train.atom optimizer, and then you can, same parameters, but just go ahead, try that, or make sure you're working on TensorFlow 2 if you're using this, or TensorFlow 1 if you choose to use the other one. Okay, so basically what an optimizer is it kind of takes this model and optimizes all the weights and biases in this for the model on this MNIST data set so that it gets a greater validation accuracy. Okay, and this atom optimizer is just one type of optimizer, and obviously we're inputting our own learning rate as a parameter. Now, what we can do is we can say model.compile, and then we're going to put in our parameter. So we're going to say optimizer is equal to optimizer. Then we're going to say loss is equal to a sparse categorical cross entropy. Okay, now I wouldn't worry too much about this, but this is just one type of loss. Once again, you can just kind of search that up and search up different types of losses to see which one works best for you. I'm just going to use this for now, and we're going to send in our metrics as our accuracy. Okay, so what this is going to do is it's going to compile our model and feed in the optimizer. Okay, and then next we need to actually give it a total number of epochs. So we're going to say 10 for now, or actually let's give it 15. So epochs, what that means is it's just going to say how many times do I actually, or how many times does the neural network actually look or see at all the training data, or all the actual images, right? And so you'll see exactly how that works when I print it out, and I'll explain that in just a little bit. Okay, so we'll say history now. History is going to equal to a model.fit. So this is where we actually fit our model and whatever it compiled onto the training data set. So we're going to pass in train X, train Y. So once again, that's our training data set with the images and the labels. Then we're going to say our batch size is equal to whatever batch size we had initially set. Okay, and then epochs, epochs is going to equal to epochs. And our validation data is going to equal, spelled that wrong. Okay, so our validation data is going to equal to our testing data set for our purposes. Test images and test X, I should say, and test Y. Okay. Now let's go ahead and run that. Hopefully, optimizer, where did I spell that wrong? There. Optimizer, there. There we go. Okay, so yeah, right. So now what you can see is that it's actually running our neural network model on this MNIST dataset. And when I mentioned this epochs 15, and you can see epoch 1 out of 15, epoch 2 out of 15, basically what it's doing is it's running through all the training dataset for 15 different times. And it's calculating, okay, what was the accuracy I saw, what is the validation loss, accuracy loss, so on and so forth. And this 469 number is basically how many different batches are there per epoch. And so in our training data set, we have 60,000 values. And so this 469 number is basically going to be 469 divided by our batch size, or sorry, 60,000 divided by our batch size, which gets us 469. So basically this is the amount of batches totally. And so you see it runs 15 times, and as you can see on the total right hand side, our validation accuracy is slowly increasing. Now I want to show you one more thing, which I think is a little important as well. And what we're going to say is plt.plot. And now all we're going to do is plot the actual values, or over time, how these validation accuracy or validation loss changes. And typically, whenever we're actually like using, or actually like seeing the data or how well the neural network ran or trained, we want to use our validation scores. And so what we're going to say is validation history, history.history, and then we're going to say val accuracy. So basically what we're doing here is we're going to plot our val accuracy values on a plot, and we're going to say plt.show. Okay, so you can immediately see here that there's a steep incline right about here, and then it sort of wavers off. So this is an important part about neural networks, in that the neural network over time, if you just keep running it an infinite number of times, you're not still going to get 100% accuracy. And the reason for that stems from these hyperparameters. And so basically, that's why hyperparameters are really important to set, because you want to try getting the highest possible accuracy in the long run. Because neural networks, what happens is that it'll increase really fast in the very beginning, but then it'll start to taper off and kind of remain stagnant for a really long time. And so choosing hyperparameters comes to be really important in that sense. Okay, so right now what we're doing with our model is we're just inputting very basic dense layers, and next time what we're going to be seeing is how we can also input convolutional layers. And you'll see right now we're using these black and white images, but in the future we also want to use colored images, right? So we're going to be using the cipher data set, which is essentially a whole new data set. Instead of digits, you're actually kind of predicting different like objects like cars, animals, and those come with colors, and so each color represents a different value, and so we're going to see how to do that and use those with neural networks, and how convolutional neural networks prove to be a much stronger form of a neural network, so it gives much higher accuracy. But for now, hopefully you can go ahead, kind of run this on your own data sets, also kind of tweak the hyperparameters to see which one works. Hyperparameters usually kind of depend on the model and the different training, and kind of just intuitively have to figure out, are there different algorithms out there that can do this as well. But for now, definitely go try out these different neural networks, and I can't wait to see you next time.